Let us look at composition rules relating to convex functions. So these are very useful when verifying the convexity of certain functions. First, consider the scalar case. This case is simple to consider and provides us a lot of intuition. So let's say that f of x is equal to h of g of x. So this is a composition between h and g. Another way to write it as h composed with g of x is another way of writing it. So when is f convex? So the question is that when is f convex? Now what we will do is we will provide sufficient conditions, not necessary conditions. So we will provide sufficient conditions under which f is convex, which means that we will provide some conditions. If you verify those conditions, then you can conclude that f is convex. But for f to be convex, it is not necessary that those conditions hold. F may also be convex without those conditions. Okay, so what is the sufficient condition? Let's take the second derivative of f. So we use the second order property. So let's take the second derivative of f. Second derivative of f is given by, let's apply the chain rule twice. So we can write it as second derivative of h at g of x, g prime of x square. So g prime is first derivative, double prime is second derivative, plus g double prime of x, h prime of g of x. Right, so this is simple application of chain rule, and this is f double prime of x. Now when is this positive? Of course, it could be one of these terms could be negative and the other term positive, and so that the sum is positive, but we are not considering that case. Let's consider a simpler case when both of them are positive. If both of these terms are positive, then definitely f prime of x would be positive, right? So let's say that, that would be our sufficient condition. So sufficient condition is that h prime is greater than equal to 0, right? So that this term would be positive. G prime of x is automatically positive. And the second thing is g prime is greater than equal to 0 and h prime is greater than equal to 0. So dot, I've just written dot because I just want to say that whatever value I plug in, it should be positive, right? Now this is another way of saying that h is convex, and this one is another way of saying that g is convex and h prime is greater than 0 means h is non-decreasing. Right, so if all of these terms are positive, then f double prime is positive. There's also another possibility. The other possibility is that g prime is negative, but also h prime is also negative. Right, so in this case, g is concave and h is non-increasing. So if either of these are true, if either 1 or 2 are true, plus this first condition is true, so this is 2 first and 2 second, and the first condition is true, so in that case f would be convex. So just to summarize, we require that g convex, h convex, non-decreasing, or we require that g concave, h convex, non-increasing. So in both these cases, this implies that f is convex. Of course, the converse is not true. So f can be convex even if these conditions are not true. But these are sufficient conditions to ensure that f is convex. And these are general, although we have verified using the second order condition, these are also true when f is not non-differentiable. So you can actually verify these conditions using zeroth order condition also. So these are true even when it is zeroth order, using the zeroth order condition. So let's take some simple examples. So remember, the outer function always have to be convex, but the inner function can be convex or concave, provided that h is non-decreasing or non-increasing. Okay, so let's take a simple example, e raised to the power g of x. Here h is e raised to the power y, so h of y is this, and g of x is any function. So now when for this to be convex, we can see that this is convex and non-decreasing. This is non-decreasing, in fact it is increasing and convex. So therefore e raised to the power g of x would be convex if g of x is convex, right? So if this is convex, it would imply that e raised to the power g of x is convex, right? So whenever you apply a convex non-decreasing function on the outside, then you can ensure that the resulting composition is convex. A similar example is minus log of g of x. So minus log is also convex and non-decreasing, right? So same way, if g of x is convex, then minus log of g of x would also be convex. Now the composition rules demonstrate a shortcoming of the way in which we have defined functions actually. The functions so far we have defined going from Rn to R, and so far we have always defined functions going from Rn to R with certain domain. But that is not actually sufficient, and that is demonstrated by this rule here. So in convex analysis, this idea that functions go from Rn to R is not sufficient. We need something more than that. So let's take a simple example. Let's take a simple example where whatever we have concluded from here fails completely. So all this rule will appear to not apply at all. So let's take an example. Let's take h of x equal to x such that domain of h is 1, 2. And let's take g of x equal to x square, right? So that, and domain of g is R, right? So here I've restricted the domain of h. So what is h of g of x? You can see that it is equal to x square for what is the domain of this function, f of x? So the domain of f is equal to the set of all x such that gx is in the interval 1, 2, because we also want the h to take values which are well defined, right? So this is the set of all x such that gx is between 1 and 2, or x square is between 1 and 2. Now first observe that h is convex clearly because it is linear, so also concave, and it is non-increasing. This is also convex. So as per our rules, and both have domain which is also convex. So as per our rules, we should have been able to conclude that f is convex. But if you look at the domain of f, you can see what is this domain. This is actually the interval minus square root 2 minus 1 union with the interval 1 square root 2. Right, so these are two disjoint intervals, and such a set cannot be convex. So this is not a convex set. So this is not a convex set. In other words, domain of F is not a convex set, which means that F cannot be convex. Right? Even though from our rules we are able to conclude that F is convex, in reality F is not convex. This means that our rules are not correct. The rules that we have derived are not correct. The contradiction is occurring because when deriving the rules, we did not pay attention to the domains of various functions at all. So we did not pay attention to the domains while deriving the rules. In practice, it is actually possible to circumvent this situation by redefining the functions to take values over the extended real line. Right? So R is the real line, and it includes all the points between infinity and minus infinity. But there is also the extended real line, which includes the points infinity and minus infinity. So the extended real line is all the points between infinity and minus infinity, including infinity and minus infinity. In other words, instead of requiring x to take values over the real line only, we will now allow x to take values over the extended real line. But of course, if there is a continuous function, it won't go to infinity at all. So we will actually define f to be infinity in certain scenarios. So this is the extended function value definition. So extended function value f tilde of x is defined as f of x for x in the domain of f, but infinity for x not in the domain of f. For convex, so this is all for convex functions. So for convex functions, we define it like this. So in other words, what we are saying is wherever f is not defined, the points that are outside the domain, let me define the value of f tilde of x, which is the extension of f, to be infinity. Right? So f takes certain values in some domain, and outside it is simply infinity. Right? So it looks something like this. In a similar way, for concave functions, we define the extended function as minus f tilde of x taking value minus f of x for x in the domain of f, and infinity if x is not in the domain of f. So for concave function, it is similar definition except that I use minus f of x to define it in a similar way. So concave function, the extension will take value minus infinity instead of infinity. So these are the extended function value definitions. And if you actually use f tilde, h tilde, g tilde in all these definitions, then you would see that everything would work out. So let us revise our composition rules. So the revised composition rules are as follows. So we are saying that g tilde convex, h tilde convex, and non-decreasing, or g tilde concave, h tilde convex, and non-increasing. So the rules are exactly same, except that I have replaced g with g tilde, which is the extended function value definition for g, and h with h tilde. So in both cases, I say that f is a convex function. And this will also resolve our problem that we were having in this example, because in this case, observe that h of x, which is defined like this. So what will be the h tilde of x? So h of x was x and the domain of h was 1, 2. So h tilde of x would be equal to x for x in 1, 2 and infinity for x not in 1, 2. And therefore, although the function h in its domain is a non-decreasing function, yet the extended function value definition of h tilde shows that this is not non-decreasing. So it is not a non-decreasing function or not increasing either, right? So because it is infinity somewhere, then it is varies from 1 to 2 and then again becomes infinity. So either this is neither an increasing function nor a decreasing function, and therefore this definition does not apply to it, and hence this contradiction does not arise. So we should use the revised composition rules whenever we are dealing with functions whose domain is not Rn. So any function with a domain 1, 2, a, b, its extended value definition will never be increasing or decreasing. So this kind of extended function value definition is very common in the context of convex analysis. It's not used in other areas of mathematics as much it is used in convex analysis. Finally, let us come to vector composition, which are slightly more complicated rules. So vector composition rules are as follows. So let us consider a function h of g1 of x, g2 of x till gn of x. So x is in Rn, and then you can say that g can be a function. So gi is a function from Rn to R. So I can say that g is a function from Rn to Rm, where there are m functions. So this can also be written as h g of x. I have put underline with g because I want to say that g output also is a vector. So the result here, so the composition rule here is that we require gi tilde to be convex and h tilde to be convex and non-decreasing in each component. So it has to be non-decreasing in each component, which means that it depends on m components, right? So in each component it should be increasing. So if you fix the rest of the components, increase one of the components, then it should be non-decreasing. And the other rule is that gi tilde concave, h tilde convex, and non-increasing in each component, right? So under these two rules we have that f is convex, right? So the vector composition rule is slightly more difficult to apply, but is nevertheless very, very useful. So for instance, consider the example h of x equal to max of xi. So this is a pointwise maximum. We already know that this is convex, and let us consider g of x or gi of x as e raised to the power xi, right? So here also we know that this is convex. So therefore, what do we conclude? And what can we say about h, whether it is non-decreasing or non-increasing in each component? So you can see here that h, if you increase one of its components, let's say you increase x1, once you increase x1 beyond all other components, h of x will be equal to x1 after a certain point, and then from there on it will keep on increasing. So you can conclude here that it is indeed non-decreasing in each component. So therefore the first of these rules are applicable, which implies that this thing max over I e raised to the power xi is a convex function.